Okay, I'll go over the answer. I'll just read out the answers, guys. Just keep in mind when I read them out of the book solves with all correct sig figs. So if your answer is not exactly 100% the same as mine, but really, really close, you're fine. Okay. If you think it's too far away, you feel free to ask, and I can tell you. But you don't have to ask every time. If you're like within like a very, very close number to it, you should be fine. If you know how to use the system. But let me read them all for the whole set of 7 first, and then we'll take questions after that. One other quick thing. In 18, I had a few people early this morning ask me about 18C. I usually tell everybody not to do that one because we'll discuss it when we get to it. I just forgot to when I assigned it yesterday, so don't worry if you were confused on what you were supposed to do for 18C. So anyways, number 6, the first one I assigned, should be around 8 meters per second squared. You need the correct unit as well. Number 8 should be around 3 meters per second squared. Number 10, about negative 0.28 or 0.3, depending on how you round. Something close to that, meters per second squared. 18, part A, 1 meter per second. 18, part B, negative 1 meters per second. 20, 5.1 seconds. 26 was the next one, right? 26 is about 8.8 seconds. And 28 is 6.3 seconds. So questions on any of them? Trish? Maybe it's because you rounded. What number was that? One. Oh, never mind. I was looking at the answer there. 26. So you got 9, you said? And the answer should be 5.1. You want to see it? Okay. So we're going to jump to number 20 on page 65 since there's a question on it. It says a car accelerates from rest at a constant 5.5 meters per second squared. How long will it take to the car to reach a velocity of 28 meters per second? This is a good example, one where I said yesterday, if you know your units well and pay attention to that, there's a common mistake year after year on this one. I don't know if you made it or not, but it just comes to mind that when it says constant 5.5 meters per second squared, that doesn't mean constant velocity, first of all, because 5.5 meters per second squared is what kind of value? Yes, that's an acceleration. So that just means the acceleration is maintained as that. But remember, anyways, in this course with algebra, we assume if there is acceleration, it's going to be uniform or constant anyway. Don't get confused with constant velocity versus constant acceleration. Because if it was constant velocity, acceleration will be what value? Yeah, 0. Okay, so those are two completely different things, saying constant velocity versus constant acceleration. Okay, so watch out for that. It does start out right away telling me it starts from rest. So what do I list for that? 0. So we got VI is 0. A, and it didn't jump right out and say this is the acceleration, but because of that unit, it has to be, right? How long will it take for the car? So how long means find time, obviously, to reach a velocity of, clearly that's a velocity, because it says it, and we reach it, so that's our VF, 28 meters per second, and we're looking for time, how long. Remember what I said yesterday as well. Watch out. Just give it an extra thought before you move on past the givens. Sometimes we might have to put a what on the given acceleration. What did I say? Watch out for. Sometimes on the acceleration, we might have to make it what? Yeah. Negative. Do we have to here? No. We're always assuming we're going in the positive direction unless told otherwise. So if we go with that, we're starting from rest, going in the positive direction, so getting up to this speed. So obviously we're speeding up, right? Didn't say those, but what's going on definitely seems like we're speeding up, right? So if we're speeding up in the positive direction, my A would stay positive, right? So we don't have to do that, but we have to always consider that. If we don't always consider it, we might miss it sometime, right? Alright, so we got all our givens. Then which equation, 1, 2, 3, or 4, are we going to list as the useful equation? The list we gave them in the notes. Which one? Trish? 1. And 1, the way it's given, looks like this, right? So we need to solve it for t. You may put in zeros before rearranging. That's 0, right? So therefore, VF equals AT, if that's term 0. And we just got to divide over A. So T equals VF over A. The time that it takes for this to happen is going to be 28 over 5.5. Are our units all good before we go any further? Yeah, meters per second squared, meters per second, everything meshes there. So if I divide these, that's how you should get around 5.1 seconds. This is time. You good on that one? Any other questions on that one? Any other questions in general? Yeah.
I was going to ask you.
Sure. This is one this morning a few people stopped me to ask me about as well. Remember something I said maybe at the very end yesterday? I'm never going to give you a problem that's unsolvable, but you might have problems that have more than enough or extra information. This one had some extra information. And if you accidentally used some of it and didn't truly start to think about what it's asking you, you could have easily missed it. So the answer we should be getting is around negative 0.28 or 0.3 around there, meters per second squared. It says we're jogging to a bus stop for 2 minutes at 3.5 meters per second. When we look at our watch and see that we have plenty of time before a bus arrives. Over the next 10 seconds, we slow our pace to 0.75 meters per second. What was his average acceleration during this 10 seconds? Let me read that one more time. The last sentence. What was his average acceleration during when? The last 10 seconds only. So does the first 2 minutes really matter? No. So if you use t equals 2 minutes in your calculation, you're not going to get this right. Because the acceleration only occurs at the final 10 seconds, so that's what this is asking about. However, we don't need that t of 2 minutes, but we do need to know what was my initial velocity when I did start, that I slowed down from. What was I going initially? Once I started to slow down, huh? Good. The 3.5 matters. I was running for 2 minutes at this speed. Then I slowed down. The 2 minutes doesn't matter, but that does, right, as my VI. Make sense? Then I go from that to a velocity of 0.75. That's going to be my final meters per second. And I know it took 10 seconds. And I want to know the acceleration, right? That's pretty clear. Just straight up ask you that. So with all those in mind, we look like we got equation 1 again, right? Solve for A this time, though. VF equals VI plus AT. Nothing 0. Rearranged from there. A equals VF minus VI. And then divide by the T is how we solve for that one. Plug in the numbers. And we got 3.5 minus 0.75. Units are all good, by the way. I already looked at that. Divided by 10. And, oh, I took that, didn't I? Hold on. I plugged in these factors. I just thought 0.75 is my VF, right? So the 0.75 goes here. 3.5 goes here, making it a negative number, which should make sense. I'm slowing down. I'm going in a defined positive direction, right? In order to slow down, if I was going positive, this better come out what? Negative. And that's how you get about negative 0.28 meters per second squared. You okay on that one? Yes. 18. Okay. So for number 18, remember, don't worry about part C. We'll just kind of discuss why they asked that, but you don't have to write anything down for it. I meant to tell you don't worry about that. And in number 18, it says a golf ball rolls up a hill towards a miniature golf hole. Assume that the direction towards the hole is positive. So we had our one example yesterday was something rolling up, right? told something, if we're told one direction's positive, we got to stick with that. So you got just something rolling up, and going that way is the positive direction, right? If the golf ball starts with a speed of 2 meters per second, this is part A. All right. So that obviously means the V initial is 2. So something must have hit it to make it go up, but whatever it did, it has an initial velocity of 2 meters per second, right? And slows at a constant rate of 0.5 meters per second squared. Meters per second squared, that's the acceleration. So here's where we got to be careful. Probably the reason why this one's missed the most. What do I got to do to that A? Yes. Put a negative on it. Because, remember what it already said, up the hill's positive, right? If I'm going up and slowing down on the way up, then A's got to be negative. That's the only way that could happen. Again, that's why we learned that in the past, so we can apply it in these kind of situations. And we want to know its velocity after 2 seconds, a t of 2 seconds. Units all look good. We got meters per second squared in seconds. So we essentially want its final velocity, right? At the end of that interval. So we list that as our unknown. And early on, most of these have been using equation 1. Then we mixed it up a little more later. But equation 1 still is VF equals VI plus AT. This time we're solving for V. Well, it is solved for VF, so we don't have to rearrange it. We can just plug in the numbers. 2 plus negative 0.5. We had to make that negative. So that'll be 2 minus 1, essentially, which will be 1 meter per second. Now, this, it didn't ask you to think about it right now, but we still should. When you roll something up a hill, eventually it's going to do what? Come back down, right? Unless it reaches the top. But if it doesn't, it's eventually going to come back down. We can at least know something about this situation. My V that I solved for came out positive, didn't it? If it came out positive, it's still going what way after 2 seconds? Up, right? If it came out negative after 2 seconds, that means at some point it turned around, which could happen. But it didn't at 2 seconds at least. So, but based on that idea, it asks me to do this one more time. I'm not going to relist all the givens since most of them are the same. Just any new ones that matter. So we got a new t. Now we want to know the same thing, but after 6 seconds, right? Same equation. We're just changing the t. So I'm just going to go right to plugging in since it's really the same problem, just running it with a different number. So we still have a VI of 2. We still have an acceleration of negative 0.5. And now the t is 6. 6 times negative 0.5 is negative 3. 2 plus negative 3 is going to be negative 1 meter per second. So by the time 6 seconds happens, making sense of this, it's negative, right? And that means it's on the way down. And basically, all C was, by describing the motion, was just thinking about what we just discussed right there. Just thinking about the fact, well, after 2 seconds, it was on the way up, and by the time 6 seconds came around, it was on the way down. It didn't ask me to do this, but just an FYI, we may eventually run into this. It could ask a variation and ask me, how long did it take to stop? Because before it comes and turns around, for a moment it has to stop, doesn't it? If we're ever asked that, how long it took till it stopped before it came back down, we would set VF equal to what? Yeah, 0, because it would have to stop for a second. And then based on those values, if asked, we weren't, but if asked, we could find how long it took to get to that turning point. We good on that one now? All right, other ones, anything? Yes. 28. On page 69. A car accelerates at a constant rate from 15 meters per second to 25 meters per second while it travels a distance of 125 meters. How long does it take to achieve this speed? So 2 numbers in meters per second. The first one's got to be the VI, right? 15 meters per second. Then we get up to a speed of 25 meters per second. The D that this occurs over, how far it went while doing this, was 125 meters. Units still all look good so far. How long does it take means find t, right? So looking at our equations, which one equation will work for this one? 1, 2, 3, or 4? Go ahead. 4. And 4 looks like this originally. D equals 1/2 VF plus VI times T. Nothing's 0, so we'll just rearrange as is. To get T, the first thing to do is multiply 2 over to get rid of the 1/2. So that'll put a 2D over here. Once that's moved, remember this is a quantity. That whole thing is multiplied by T, right? That whole set of parentheses. Therefore, I could divide that whole set of parentheses over in order to get T by itself. And that's what we could plug into. So T will equal 2 times 125. And remember what I suggested yesterday, because one of our examples had some division in it? To avoid making miscalculator errors with longer calculations, because there'll be one bigger than this in the future, and not get a calculator error for like wrong order of operations, I suggested to do what? Yeah, basically figure out one single number with the numerator, figure out the denominator like it's a separate thing, then divide. If you don't want to do that, the only other thing you could do, so you don't make a calculator error, is put the entire numerator in parentheses divided by the entire denominator in parentheses. Then it should do it right. I really suggest, especially if you're having trouble, do the top separate. So 2 times 125 is 250, right? And then the bottom, 25 plus 15 is 40. So 250 divided by 40 is 6.25 or 6.3, depending on how you rounded that, okay? Like I said, you could round it 1 or 2 non-zero decimal places. So either one would be fine. Are you okay with that one? Any others? All right, so, I mean, for the most part, these are all about, so far we haven't seen any conversion ones, but just watch out for that. Always look down and make sure everything's in the same unit. If not, you got to convert. And we want to always convert unless told otherwise. So we end up with like meters per second, seconds, things like that. So if you were ever given a velocity in like kilometers per hour, remember very early on this year, like first week when we worked on conversions, we went over how to change kilometers per hour to meters per second. If you forget how to do that, it should still be in your early notes somewhere. All right? That will come up at some point, even though it hasn't yet. You know, seconds to hours, hours to seconds, that kind of thing you should be able to do as well if necessary. All right. I'm going to take a minute to just discuss one more of the kinematic equations. Throughout the week, we'll keep picking one to figure out where it came from. So kinematic equation number 1 came from the slope of a VT graph, right? Because if you rearrange it, we said A equals VF minus VI over T is really, when you break it down, that was really the slope pieces of a VT graph. So you don't really even have to write this down. I'm not going to test you and say, prove where this came from. Not in this course. But I want you to know that it came from somewhere. And if you really want to write this down, you can, but you totally don't have to. Just pay attention. All right, so I'm just going to rewrite kinematic equation 2. And it comes primarily from a graph that we already studied as well. All right, so kinematic equation 2 said D equals VIT plus 1/2 AT squared. Just keep that up there for now, just to refer to it. Somewhere not that long ago, we went over what it meant to take the area bound to the x-axis, or the p-axis in this case, of a VT graph. Does anyone remember what the area represented? Yeah. We'll say it more specifically, displacement. Okay? You guys remember one day we had to do that? It was on your one study guide. And we didn't spend a lot of time on it. But knowing that is important, how to derive this formula. All right, so let me give you a VT graph, an example one, to prove this thing here. I'll give you an example of a VT graph that has uniform acceleration. But we should remember generally what that looks like. If there's acceleration occurring on a VT graph, in general, it has to take what kind of form? It remembers from VT graphing. Well, I told you, what kind of graphs won't we have on VT graphs? Curves. We won't have curves. So that leaves us only two options really now. Yes? All right, a linear line, but if there is acceleration that's non-zero, that linear line is going to have some kind of what to it? Slope, right? Some kind of non-zero slope. So this would be an example of an object that has a positive acceleration. Why? Because the slope's positive, right? And did this object start from rest? No, because if it did, it would start from here, though, right? But in order to prove this full equation, if we use this equation, the objects start from rest, what would happen to this whole term? It would be gone, all right? So I'm picking an example of a graph where that would keep that hanging around. You'll see why in a second. All right, so this equation happens to be solved for D, right? So I'm going to drop down a line that binds this graph to the x-axis. And that is what kind of shape? A trapezoid. And we said that nobody in here is going to probably remember the area of a trapezoid. That's okay, because you could break a trapezoid like this one into what two shapes? Go ahead. All right, a triangle and a rectangle. And we could find this area and this area separately, right? Those are easy areas. We can all remember those. So let me make some other points on here before we get going. I'm not going to put specific numbers here. However, that point right there on a graph would be the initial velocity at time t equals 0, wouldn't it? So whatever number is there, it's some positive number because it's above the x-axis, right? Whatever number that would be, though, that would be a VI, wouldn't it? Wherever the time interval ended, right there, that V would be what? VF. Everybody see what I'm saying? So that would be your VI, and whatever number would we be able to read there on one of these graphs would be our VF. And well, keeping that in mind, now let's find the areas. How do we find an area? Let's go with the rectangular region first. Okay? Length times width, we said in the past, right? We should all remember that. So, if this is 0 right here, this whole thing's just whatever time interval t everything's happening over, right? Everybody agree? And if that was 0 to here, this whole side will be whatever value VI is, won't it? And when we multiply those terms together, we would get VIT, wouldn't we? Is that a coincidence so far? No. All right. Now let's go over to the triangle. All right. So the triangle, this side, which is the height of the triangle, right, is the difference between this number and this number, right? If we wanted the height of this triangle, wouldn't we take whatever this number is here, subtract it off that, and we'd get here to here, right? So couldn't we call that side VF minus VI using variables? Everybody agree? That whole side is VF minus VI. And the base of the triangle is still what? Time, right? Now this isn't going to immediately look exactly like this. But you could probably guess where that 1/2 came from. What's the area of a triangle? 1/2 base times height. Or from what we just got here, wouldn't it be 1/2? It doesn't matter the order, height times base or base times height, it doesn't matter. 1/2 VF minus VI times T, right? Now wait, that doesn't look exactly like that, does it? But now we could do something else, a little substitution. Let's go back to one we already proved, the first kinematic equation. VF equals VI plus AT, right? I'm going to do a little rearrangement and subbing of this one. Well, I'm going to subtract VF over to the left, or VI over to the left. That's legal, right? I'm allowed to do anything to an equation I want as long as I do it to both sides, right? If I subtract it up here, it cancels here and moves over, and I could get VF minus VI equals AT. So from the earlier known equation, from the slope of a VT graph, we could just redefine VF minus VI as AT. If they're equals, they're the same thing, right? So if that's the case, up here, 1/2, I could replace AT for this VF and this VI, right? But there's already another what here? Another time there. And T times T is what? And that's 1/2 AT squared, isn't it? And now that's that piece, isn't it? So that's essentially where that comes from. It didn't come out of thin air. Every equation has a reason where it came from. I'm not going to ask you to prove that, but you should always know where something came from, not just have them thrown at you and say use them. We'll do a quick proof of the third one and the fourth one tomorrow or Friday. All right. All right. For the remaining time, I'm just going to give you another practice set, pretty much most of the odds through that set, just to practice one more time on these. So hopefully after fixing the ones that some of us had questions on, these will become simpler. Keep watching out for the possibility of too much information. Okay? So I'll write these down. After we're done taking questions on these tomorrow, we're going to move on to, we're not going to get fully through them, but we're going to move on to something called two-part problems. Exactly what it sounds like. There's going to be two separate parts that have to like come together. But we won't be able to finish those in one day. Friday, you're going to have a short quiz. All right? Anything new we do tomorrow will not be on the quiz Friday. So those are going to be like a 2, max 3 problem quiz on Friday. You should have enough time in 18 minutes to do 2 or 3 problems, just like the ones we're doing right now. Okay? Just to make sure we got that down before we move into some harder stuff. Alright, so anyways, back to page 63 again. I'll write them up here. Write these down. You could use the rest of the time to start. Or 64, so page 63. We're going to do 7 and 9. I'm not going to worry about 11 and 11. 7 and 9 on page 64. Page 55, 19 and 21. And page 69 again. Two odds we didn't do on that. 27 and 21. There's 6 of them. Start them now. Hopefully we'll get over them pretty quick tomorrow because we already went over a set stuff. Okay.